Okay, so welcome to week 2, this lectures and lecture 6. This lecture is mostly on the concepts and application of different units that we use in the atmospheric science, and this is going to be one of the very important lecture, and I must say that this is the basic for understanding the concept of pollutants and their concentration, reaction rates and all those things in the atmosphere. So, this is the lecture 6 that we are going to do, and just to give a recall of what we studied in the previous lectures. In previous week we covered almost like 5 lectures. In the first lecture we talked about the fundamentals of air pollution, what are the sources, effects and mitigation. We introduced about the course discipline and who should be reading this course or studying this course. Then we move forward that how our Earth's atmosphere has evolved during the period of time and how it has reached to the present day composition. This was the lecture 1. In the lecture 2 we covered uniqueness of the Earth's atmosphere. This is very important again, because Earth's atmosphere is very different or unique compared to the other planets that we have in the atmosphere. So, for example, we talked about the importance of different layers in the atmosphere and then how it reached to the present day composition. How and why these gases and then trace gases, carbon dioxide and aerosols, they are actually important and make this planet temperature habitable. Otherwise, the temperature it would not have been very habitable one. So, we with this one we talked about the radiative balance equations and then we introduced the concept of greenhouse gases in controlling the Earth's surface temperature. And then we also talked about the variation in the solar energy that is reaching on the Earth's surface, or we call it solar radiation or solar constant, and how it is varying on 11-year cycle. Little bit we have given, because this is a course on atmospheric sciences, we cannot go much beyond on that one. So, if you want to read more, then you should talk about lots of research has been done in earth sciences, especially in geology. Understanding the climate in the past, they have studied that how the solar constant has varied over time, and couple of things are very important. For example, one is 11-year solar cycle. So, that is one very important aspect, that is actually because we mostly talk about the, when we talk about the temperature or the Earth's temperature, we just talk about say previous last 200 years or so. So, in this period 11-year cycle becomes very important. Then we are also talked about the albedo or reflectivity and how they are actually playing a very important role in the in controlling the atmosphere. We talked about the albedo of different systems. Then in the lecture 3 we introduced the air pollution and the topic that on air pollution, and we also discussed here that what types of air pollutions are there. We like gaseous and particulate air pollutions. We also talked about national ambient air quality criteria for gaseous pollutants, some of the emerging pollutants in the atmosphere like volatile organic compounds or hazardous air pollutants. We also talked about that, although they have not been listed as a criteria of pollutants by the CPCB so far. In lecture 4, so this was the lecture 3, air pollution and different types. Lecture 4 we specifically talked about the particulate air pollution, and we emphasizes on the atmospheric aerosols and their importance. What are the sources and composition of aerosols, size distribution and properties of aerosols, this is very important. Then we also talked about the effect of ozone and ozone air pollution in plants, that how they can affect the productivity and other things. We talked about particulate air pollution with the emphasis on the atmospheric aerosols and their importance. It is repeating from the previous. So, and then we talked about factors that control air pollution. This is one of the very important thing. Moving on the lecture 5, we talked about again the consequences of the air pollution, and we give some of the suitable examples. For example, poor air quality and reduction in the visibility, photochemical smog, acid rain, climate change and role in rainfall or precipitation. These are the few things that we have covered. So, now we are moving actually a little bit more in the atmospheric chemistry, that was general lectures that we had. So, in this lecture, that is lecture 6, we will be discussing about the concept of colloidal or dispersion system. I will introduce this one, although I have discussed little bit in that on that one. And then we will put the concept of various units. This is, as I said, that this is going to be very important. So, please pay attention to this one. And then of course, its application in earth, atmosphere and oceanography. Little bit mostly this lecture will be on the atmospheric, but we will also cover little bit on the earth sciences, soil and then oceanography as well. Okay. So, the very first question that comes to your mind, if you look today and if you are in the Indo-Gangetic plain, you will see that okay, the pollution is high. Okay. So, what actually how can you infer that one? This is one of the very important thing that actually that how will you infer this. Okay. So, pollution are high, this you can visibly see this one. Okay. One thing is actually you can see visibly, and this means visibly you can see means qualitatively you can say that today the pollution is higher compared to the previous day or a couple of days earlier. Okay, that you can compare. This gives you some qualitative idea, it does not give a quantitative idea that how much pollution actually is there. And similarly, if you do look another part aspect, that is actually called visibility. So, if you see that okay, if the pollution is more, you will not be able to see longer distances. So, visibility will be lower. So, some sort of understanding is there that there is a relationship between visibility and the air pollution. So, higher the air pollution, lower will be the visibility. So, there is an inverse relationship. So, these are the general things actually, I mean, so qualitatively you can say. Now, there are two things that becomes very important. I said that okay, air pollution is there, and then the air pollution today is higher compared to yesterday. Now, this is actually a qualitative. How will you bring the quantitative information here? So, we will discuss that one here. Okay. So, just to give you an idea, if you want to measure anything, there are two ways to report that. One is qualitative, just I said that visibility, and by looking at the air pollution levels, you can say that okay, it is highly polluted or not. But in the qualitative one, the point is that you will not be able to say that how much it is, although it will say okay, it will identify the important pollutants. I gave the example here, very general example here, and in the quantitative one, it will not only give you the identification, but it will also the quantification of this one. So, this becomes very important. And here the very first fundamental principle that comes, that how will you measure something. So, kindly note that any specific analyte, whatever you want to analyze, it will have a very specific property, and that specific property you have to identify, or there are literature you can find it out. If you are measuring something new, that is you can create a new idea, and you can create a new measurement techniques or tools only if you know that what is the specific property of that particular analytes or the property that you want to measure. So, this is very important. Okay. And then there should be a relationship, not only that specific property you have to measure, and then you have to basically quantify based on that specific property. Then you have to establish, or there you must also know that there must be a relationship with the concentration. So, this is very important. Okay, like spectrophotometry, mass spectrometry, yeah, we discuss those things. Often same instrumental method is used for qualitative and quantitative analysis. This is important that you can use, but one will not give you the idea. For example, here I gave the example of spectrophotometer. So, a spectrophotometer can measure the absorbance and to find out the concentration of compound in a given solution using standard calibration. Okay. So, now if you measure absorbance of a compound at a given wavelength lambda, you can find it out that how much whether that species is present or not. So, that wavelength or that lambda is at which the compound absorbs, it is a characteristic property of that compound. So, that absorption at a given wavelength by the particular compound is a specific property. Okay. So, other compounds will not absorb. If there are other compounds which are absorbing in your solution, then there will be actually results will be not good, because then you are adding up or subtracting, okay, whatever way it is. So, you need to know that the specific property you have measured, and the property should be measurable. If it is not measurable, then you cannot quantify. So, this is very important. Okay. Okay, so let's see this one. For example, I just gave you very important types of different types of instrumentals that are methods that are used here, and their property. Here are the property is a very specific property, and that is very specific to that one. Okay, and then examples are methods. So, for example, radiation emission. We say that particular element is emitting a radiation at that particular. So, there actually we measure emission spectroscopy. Okay. For example, you have ICP-AES, inductively coupled plasma atomic emission spectroscopy. So, what you do actually? You do spectroscopy by measuring the emission of that particular analyte or the element or the compound. Then there are actually fluorescence, phosphorescence and then luminescence. There are different techniques where the emission is used. Kindly note that every compound either will emit the radiation or it will absorb the radiation. Okay. So, when these are the properties that are radiation emission, these are the examples or methods that are used in the radiation emission. And then if the radiation is absorbed, what are the properties or method that you can use? Absorption spectroscopy. This is very common. One of the very most common method is absorption spectroscopy. Everybody uses this one, or most of the people use this spectrophotometry, that is called, or sometimes it is called photometry. There is actually also, because of this one absorption, there is a nuclear magnetic resonance, NMR we call, and ESR, electron spin resonance. So, these are the things. Then radiation can be diffracted also, right. So, you measure the diffraction of the radiation by the specific again. So, here it will be X-ray or electron. Okay. So, X-ray radiation or X-ray diffraction you can measure, or electron diffraction you can measure. So, there are many things that you can do. Similarly, you have radiation rotation, polarimetry or circular dichroism. Electrical potential, this is again one of the very important. This is mostly used in the environmental chemistry, especially in the analytical chemistry. Potentiometry is one of the very common method, that where the potential change in the electric potential is measured because of the certain change in the chemical reactions or production of ions and other things. Then other things which is very common for ions is actually like you can measure the current. Current is very easily can be measured, and the method or instruments that are used actually are voltammetry, amperometry or polarography. These are the things that you can do. Then current and resistance, they are actually reverse. So, you can measure resistance as well, and conductometry. For example, we will be discussing here, if we have to measure the concentration of the ions, cations and anions that are there in the aerosols, we usually use ion chromatography, and there the ion chromatography we measure electric resistance, okay, or resistivity, whatever we call it. Then very emerging topic is mass to charge ratio, and the instruments or method that we use is called mass spectrometry. The last one, or there are many more actually, not last one actually. So, radioactivity, here we measure activation or isotope dilution methods. This is the different topics all together. So, I am not going to discuss this in this lecture. Okay. Okay. Now, the title is wrong. So, it should be actually measuring how to measure concentration of the atmosphere. Okay. Now, we talked about gaseous air pollution or particulate air pollution. So, in the gaseous air pollution, what is happening? Gas which is actually a dispersed phase, okay, and this is actually you measure by volume, and then another gas is also there, that is called dispersion medium, that is also in volume. Okay. So, this type of concentration are represented, what will be represented? They will be represented as volume by volume or mixing ratio. This is important, or this is also called actually a mole, okay, mole fraction, because we will discuss in the equations that we have very simple equation, Pb is equals to nRT. Okay. Here you have n is equals to directly proportional to V. So, if you measure volume, you can actually convert it to the number of moles. So, this is the reason why you use either you use volume or you measure what you call mole fraction. Here n is actually number of moles. So, if you just take the ratios, then it will be called mole fraction. So, this is very important, and not only that, if you report this V by V, then it will be either in the what you call meter cube by meter cube. Sorry, it is actually okay. Okay, so this, if you will report this volume by volume, the generally reported concentrations are called actually like ppm, parts per million. We will come to that, parts per billion, and although these units are actually used in the liquid or solution as well. So, I said that these volume by volume and or mixing ratio, they can also be represented as the mole fraction. This is one of the very important things, and we will come to that one. Okay. And then the other one is homogeneous mixture of gas plus particulate. Now, earlier system was gas plus gas. Mind it that both the cases, our system was actually homogeneous. If your system is not homogeneous, then the concentration will vary a lot. So, then reporting the concentration will be very difficult, okay, which we will see in case of aerosols. Okay. In the gases, for example, if you measure gaseous concentration anywhere, you will have nitrogen 78%, oxygen 21%, and argon about 0.9% or so, I mean similar, but the concentration they will not be varying. But if you measure the same concentration of pollutants here in Varanasi or in the Gangetic plain, and you measure in the Himalayas, the concentration will vary a lot, or similarly if you measure at the oceanic region. Okay. So, the concentration of particulate matter will vary, but concentration of gaseous species will not vary, because our gaseous system is actually homogeneous in respect to these gases, whereas this is also homogeneous, but this homogeneous is localized, not very especially scale. If you talk about on a larger scale, this is not very homogeneous. Okay. So, here what will happen, solid will be actually in the dispersed phase and gas actually is as a dispersion medium. Now, so this means gas, as we discussed earlier, we will report in the terms of volume, and then dispersed phase or mass we will solid. So, solid, any solid has actually mass, that is very important or very easy to measure. So, we will measure by mass. So, the concentration that can be reported here is actually because if it is, as I said, that homogeneous is there and gaseous is the dispersion medium. So, you have to take how much particulate matter is present in the dispersion medium. So, dispersion medium means meter cube or volume of the air you take, and then you take how much particulate matter is present in that one. So, this will be giving you the concentration in microgram per cubic meter, and the concentration will be reported as mass by volume. This is very important. Now, this is another one very thing that you must remember here. Here, if just volume becomes liquid case, you just take mass as a solid and volume take in the what liquid, liter or ml. So, it will be gram per liter or microgram per liter or something like that. The same thing it becomes like in the liquid system, it will be becoming like a ppm, you can report that one. Okay. So, this is very important here, that I said that if you see the last line, we can convert ppm into microgram per cubic meter. So, you can actually convert and vice versa, but this practice is generally adopted in the case of gaseous pollutants, not in the case of particulate matter pollutants. So, also the particulate matter you can convert it into N, because you know the total mass of the atmosphere and you know the density. So, from the mass and density you can calculate that how many number of particles were there. So, you can calculate in principle that number concentration as well. Okay. So, how then I said that we report that the abundance of aerosol or air pollutants, particulate air pollutants especially, in the unit of total mass concentration in given cubic meter or 1 cubic meter. So, this will be actually microgram. Generally, now you can say that why it is microgram, not milligram, because the concentration of the particulate matter is not too high. So, we generally report into microgram per cubic meter, but at some places the microgram concentration can be actually can reach into in such a level that you will have like 10,000 of microgram per cubic meter. So, there you can actually report in the milligram per meter cube, there is no problem. Okay. Then one very important unit is actually called aerosol optical depth. So, as the name said that aerosol, optical and depth, three terms are there. Aerosol is actually air pollutants, optical means somewhere here the optical methods has to come into the line. So, what in this case what we will do, we will have a column of air, okay, and this column of air will have lots of air pollutants here, okay. and you sign a radiation I 0, and here you have lost in the here you can get I. So, how much radiation is going by. Now, what will happen? These particles that are there in the atmosphere, they will either scatter or they will absorb. There are 2-3 things that can happen. So, they will be either scattering or they will be absorbing the radiation. So, if you just measure this one, and if you take height 0 from Z, and so in principle what you can do, generally you integrate, the term is called B extinction into dz. Okay. So, and Z, where Z is varying from 0 to Z is varying how much actually, Z is varying from Z. Okay. Oh, sorry, this is something. So, here this unit is called B extinction. This B extinction you can actually measure, and B extinction is nothing but sum of the scattering coefficient plus absorption coefficient. We will discuss this in later slides, and this is called actually AOD or aerosol optical depth. You integrate this one and varying height. So, this becomes very important. The latter parameter or AOD is defined as the vertical integration of the fraction of incident light that is scattered or absorbed over the entire height of the atmosphere. Okay. So, this is very important, and this gives a kind of spatial coverage, lots of the data you can collect. Okay. Not only that, absorption and scattering, they can be used to estimate atmospheric radiative forcing due to long living greenhouse gases as well as particulate matter in the atmosphere. Okay. Here, so I gave one example, and here is another example. So, here the concentration is aerosol concentration is reported. Of course, here the visibility is not reported, but you can see very clearly that when the aerosol concentration is low, visibility is very good, but when the aerosol concentration becomes high, the visibility reduces. So, to sum up, what we did, we used, or as I said in the measuring methods or instrumental method, how we report this one. So, we use their properties. So, what property? For example, in the particulate matter, we know that particulate matter, they have mass. Okay. So, we will actually, if we somehow can collect the particulate matter, that how much mass is there in 1 meter cube of air, then we can report that actually that concentration into microgram per cubic meter. So, collect and measure the mass. Mass is usually measured. So, we have to collect those aerosols. We will discuss in the, when we will discuss instrumentation, then we will discuss this one, that how the collection is done, and then we collect and measure the mass gravimetrically, and so we get actually mass, total mass that is collected, and then total volume we can do that one. And then because the particle scatter or absorbs those solar radiation, so we can measure scattering or absorption coefficient, and this can be used to report visibility or even the aerosol optical depth that we discussed. Okay. So, now to sum up again, in the atmospheric sciences or atmospheric research, we usually do many things, either we report in the mole or mole fraction. Percentage is also reported sometimes, but very rare cases in the atmospheric sciences. Why percentage is not reported? Because you have to take out of 100, then out of 100 means the concentration is so low that out of 100 the concentration will be, for example, say 10 to the power minus 3. So, there is no point in reporting that into the percentage. For example, CO2 concentration, this is asked actually, many people ask that why CO2 concentration is reported in ppm. Okay. Because here, if I say that what is the atmospheric composition, so what is the CO2 concentration today, so somebody said okay 425 ppm. This means, and now mind it, I said again that CO2 is actually a gas. Now, it is a gas, what will be that? So, you have to report either volume by volume or mole fraction by mole fraction, n by n. Okay. This is the 2 units that we will be reporting. So, ppm is actually, like I said, that 425 ppm. This means you have to take 10 to the power 6 molecule of air, okay, and then out of that there will be 425 molecule of CO2. So, this out of 10 to the power 6 molecule of air, there will be 425 molecule of CO2. Okay. So, now you can see that we are talking about this one in 10 to the power 6. If you have to convert this into the 100, then you have to just multiply by 100. If you just multiply, then you can get into the concentration, you can get into percentage. But this concentration will be very low again. For example, in this case this will be actually 0.0425%. Okay. So, you can report this one, still you can report, because but the concentration is too low, that we do not usually report. But for example, argon, we will discuss that argon and then what you call nitrogen, oxygen, they are reported into the percentage. Okay. So, we usually report concentration in mole fraction, percentage, or ppm, ppb and ppt. ppb means parts per billion, similar to parts per million. There will be actually in the denominator there will be actually 10 to the power 12, and then ppt means parts per thousand. Then you can also report number of molecules or moles per meter cube. This is important, and this is very important for the atmospheric kinetics. Actually, when we say reaction kinetics, this kind of things are important. And then particulate matter or air pollutant concentration, they are usually reported in microgram per cubic meter, and then they can be usually converted into one, can be converted into another one. Okay. So, for example, if I ask you which is one of the SI units, mole fraction, ppm, ppb and ppt, this is the objective question that is generally asked, or in the review you may be asked. So, mole and mole fraction are SI units, ppm and ppt they are not the SI units. Okay. Okay, let me give you an example. So, there are 4 things. Calculate the composition of the atmosphere, and calculate what is the composition of the atmosphere. If I ask, generally people will say that the composition of atmosphere is oxygen 21% or 20.9%, nitrogen is actually like 78%, argon is 0.9%. Most of the people will report this one. But here when I say that, let me see if I can put it here, nitrogen is 78% and then oxygen is 20.9%. and then argon is actually 0.9%. Now, what does it mean? People are usually confused, or most of the time students are confused, that whether it is mass or percentage. So, this means if I, for example, if I ask you that if I take 100 gram of air, so will my this concentration will have 78 gram of nitrogen, 20.9 gram of oxygen and 0.9 gram of argon, or if I take 100 molecules of air, there will be 78 molecules of nitrogen, 20.9 molecules, of course, now 20.9 molecules will not exist. So, you have to take 1000, you have to convert it, okay. So that you can have 209 molecule of oxygen, and then argon similarly 0.9. So, this is actually so either you have to report in the volume by volume or you have to report in the mole by mole. Okay. So, it is not like that. So, calculate number of moles, I gave another example, calculate number of moles of oxygen, nitrogen and argon in 100 gram of air sample. The same thing, it is percentage, 100 gram I took. So, this means it become a question of percentage conversion, but here the problem will be different, because if you take oxygen as 20.9 and nitrogen as 78, your calculation will be very different. Okay. Then I gave some example of calculate molecular weight, density, mean free path and number of molecules per unit volume, and these are the things that are given. So, you should calculate, you do some homework at your place and then do this one. Calculate total mass of the atmosphere considering the earth radius as 6378 kilometer. Okay. So, these are the question that and then calculate number of moles in the H2O in 1 kilogram. So, this is very simple one. So, you can very easily calculate. Okay, I talked about this one. So, units concentration ppm and ppb and ppt, generally they are mostly used in the gaseous species. They are very common, especially when the concentration of the gaseous species is low and at least 2 or 3 order of magnitude lower than that of the air composition. Okay. So, 1 ppm means 1 parts per million, or if you just, now this is another thing, if you just want to see micro means 10 to the power minus 6. So, you can always report that micron is actually 10 to the power minus 6. So, if I say, where I say ppm, you can report this one, ppm can be stated as micro what, mole per mole. You can report this one. This is very important. So, either you report, so this is already inbuilt is there, that this means that 10 to the power minus 6 is already there. Now, you can take moles 1 and out of how much mole is there. 1 ppb is actually similarly will be parts per billion, and billion stands for 10 to the power 9. So, nanomole per mole. ppt is similarly is actually parts per trillion. So, 10 to the power 12. And so, this is the actually general terminology, and why this can be used as a actually like in the gaseous or in the what you call number of moles, either you can use volume or in the gaseous of this one. So, because you have a equation Pb is equals to nRT, and here B is actually proportional to n. So, when the B is proportional to n, so either you report in terms of n or in terms of nitrogen n, then it is same actually, sorry B, and n is actually what is number of moles, we will discuss this one. So, you can just calculate. N can also be reported at volume divided by volume of the air at for the that is occupied by one molecule, and then you can also report at what like this one number of molecules. Now, we have to write capital N here, because small n is we have used for moles. So, n by Na, Avogadro number. Okay. So, mole fraction can be written as that how many molecules are there out of Avogadro number, and Avogadro number is actually how much, 6.023 into 10 to the power 23. So, this is actually be used for this is Avogadro number. So, out of this one how many molecules are there. So, now you can imagine this, that is very huge and complicates the things, but that complication is very important and we have to understand this one. Okay. So, imagine the number of volume of pollutants are found in 10 to the power 6, 10 to the power 9 or 10 to the power 12 volume of air for ppm, ppb and ppt respectively. Okay. For example, when we say ozone concentration is actually 0.04 ppm to 40 ppb, this means 0.04 ppm or 40 ppb. This means that if you take 10 to the power 8 molecules, here it is actually reported as because 0.04 ppm is there. So, if you just see that 10 to out of 10 to the power 8 volumes of the air, only 4 volumes will be due to the ozone. Now, you can imagine 10 to the power 8 molecules of air are there, and in that there is only 4 molecule of ozone. So, this is such a trace concentration, very minimum concentration. So, you have to report in this one. Just give a check here. This is the general composition I have given. We all discussed. N2 is actually 78.08 or 78%, oxygen 20.946, nitrogen 0.93, and then you have trace gases. CO2 is reported, old data you can see here 0.0387 percentage. Now, this is very important. So, you can report that how much is CO2 concentration. From this one you can very clearly guess. You have to just multiply by 10 to the power 6. So, you will get actually 387 ppm. Okay. So, 387 ppm concentration is there, and neon, hydrogen, CH4 they are actually much less. So, that is why they are not reported in percentage concentration. Okay. So, I say that air is about 78% of nitrogen, 21% of oxygen, 0.9% of argon. Is it mole fraction or mass fraction of its gases? So, what is that? Now, we understand that it is mole fraction, not the mass fraction. Now, the next question comes that whether can we report it to the mass fraction? Okay. Yes, because mass and moles are related to each other, we can do. Since 1 mole of nitrogen actually how much? Actually 28 gram per mole, because you know like you have what you call concentration or concept of the moles. Hence, 0.78 moles of nitrogen will be 0.78 into 28 gram. This much will be, this much gram will be there. If you take 1 mole of air, then there will be 0.78 into 28 gram of nitrogen. Now, I am talking about the mass. Similarly, if you take and since 1 mole of air is actually how much? What is the molecular weight of air? You have to calculate that one. I gave the previous example and it turns out to be 28.97. Just do the calculation. So, mass fraction of nitrogen, how much will be the mass fraction of nitrogen? it will be 78 into 0.78 into 28 divided by the molecular weight of the air. What is the molecular weight of the air? 28.97. So, this turns out to be the concentration will be turning out to be like 75.56%. Okay. And what is the mole fraction of the nitrogen? Mole fraction of nitrogen is actually 78. So, we are already missing about 2.5% here. Okay. 3.5% in or 2.5, yeah. So, 2.5% is actually mass is lower compared to this one. Similarly, you can calculate mass fraction of oxygen, it will be 23.16, but if you just see in the earlier calculation, it was what is the mass fraction of oxygen is actually 21. Okay. And now see the calculation, here the molecular weight is playing very important role. If the molecular weight was lower, then this ratio would have been lower than 21. Okay. And then mass fraction of argon you can calculate 39.95 is the atomic weight of the argon. So, you can calculate, and then 28.97. So, there will be actually 1.28. Okay. So, if you just see this one comparison of mole or mass fraction of gases in the air, when I take mixing ratios or dry air or mole per mole, nitrogen is about 0.78 mole per mole, oxygen is 0.21 mole per mole, argon is 0.0093. There is a mistake actually, it should be 0.093. So, 10 is extra type of mistake here. So, this argon, just I repeat again, argon is actually 0.093, not 0.0093. CO2 is actually 380 into 10 to the power minus 6 ppm or mole by mole. Okay. So, if you just calculate this mass fraction, it will be 0.78 will be actually like 0.75, 0.21 mass mole fraction will be 0.2, and 0.093 will be almost like same, not much change, and CO2 will be much reduced this one, because it will be very slow, very low. Okay. And if you just sum up, because number of moles has to sum up to 1, number of moles of all the species that are we calculate are mole fractions, sum of the mole fractions should be 1, and if you see here sum of the mole fraction is 0.999, which is pretty close to 1, but here you have 0.967. You don't, if you just calculate mass fraction, you don't get very close to the mixing ratio or 1. So, mixing ratio or mole fraction sums up to 1, pretty close to 1, and which is very correct, but mass fraction does not add up to 0.21%. Therefore, you have to be very careful that what kind of concentration you are reporting. So, I stop here, and I think you should do some homework, some calculation at home that I have already given to you, and once you do the calculation, then we can discuss further in this next lecture. So, in the next lecture we will discuss that how other things are reported, because this concentration and these units are very important in reporting, for example, tropospheric ozone concentrations, okay, and then AOD and other things. So, we will discuss in the next lecture. Thank you so much. Thank you.